Okay, so this is chapter 6, which is about chemical reactions. So when we talk about chemical reactions, that usually involves some type of chemical change that has occurred. And if you remember, chemical changes are when we start with something and we really end with something that's fundamentally different. The key there is you can't get back anything that we started from by any type of physical means. You can't, freeze it, boil it, do any of those types of stuff, filter it, and get those original substances back. So a lot of times we have some clues to some type of chemical reaction occurring, a color change, for example. We mix a couple of solutions together, we get some different type of color that's formed. A solid being formed, which is sometimes referred to as a precipitate or PPT. Bubbles being formed. So when you do some type of reaction and you do see the bubbles start to develop, that usually means that some type of gas has formed here as a result of that chemical reaction occurring that wasn't there to begin with. Other sort of signs of chemical reactions are heat and also a flame being produced, obviously, is a pretty good sign of that. Heat as well, if you're holding onto a test tube, again, as we talked about maybe in the energy chapter, that test tube feels hot to you. That means that reaction is exothermic, it's giving off the energy, and your hand's basically picking up all that energy, which is why it feels hot to you. And vice versa as well. If you're holding onto a test tube, it starts to feel really cold. That would be more like an endothermic reaction. It's just basically sucking the energy out of your hand, and that's why your hand starts to feel cold when you're holding it. As we'll talk about more in the next chapter as well, that sort of ties into this chapter, there's really kind of 3 reasons why a reaction takes place. And that really is the formation of a solid or a precipitate being made, the formation of water, and really an electron transfer. So as we'll talk about, pretty much any reaction that you look at will boil down to pretty much one of those things happening in that reaction. And that's really sort of the main reasons, why a reaction will actually take place. And even though we may call it some different names, ultimately one of these 3 things are sort of happening. As we'll talk about, when you can classify reactions, you can classify the same reaction in many different ways. But again, everything sort of boils down to these 3 things: solid being formed or precipitate, water being made, or some type of electrons being transferred from one substance to the next. So here's some examples. Dropping the 9-volt battery in there, clearly forming a lot of oxygen, hydrogen gas there as forming bubbles. Doing some type of addition here, we have kind of a pink solution, a blue solution, kind of a purplish as they come together. It implies that perhaps a new substance has been formed when it does come together. You'll do something like this week, I think. We'll make a precipitate. Yeah, it'll be yellow as well, I think. So I'll mix a couple of solutions together and out will come a solid or a precipitate. A reminder that a precipitate does not have to be like a rock hard solid that just drops to the bottom or anything like that. Most of the time, a precipitate, like if you do a reaction, thing gets cloudy, there's some stuff floating around that wasn't there before. Those are all examples of a precipitate. If you ever want to sort of compact your precipitate, you could oftentimes centrifuge your test tube and it'll bring all your solid down to the bottom and stuff like that. But a lot of times people see it and go, well, just some stuff floating. That's not really a solid, because we think of solids as like something rock hard and just going to sink like a rock to the bottom. So again, any type of cloudiness that forms when you mix some solutions together definitely is an example of a precipitate being made. Calcium water here. Similar to, I think we looked at potassium water, I think maybe. Methane burning here is a combustion reaction. So when you light your Bunsen burner there with your inner cone, you have a combustion reaction happening. Obviously, that gives you a flame, that gives you heat that's coming off, all evidence of some type of reaction occurring. Here's our zinc with our bubbles. I think we might have done this one as well. Those maybe the one where you put your finger over the test tube, right, and tested it as well with the wooden splint. So one way that we represent chemical reactions occurring is to use chemical equations. And a chemical equation basically shows what is happening in a reaction. And when we look at one here, like hydrogen gas plus some oxygen makes some water, this is what we look at. And as we will see, basically the starting material are reactants, and they always go to products when we look at a chemical equation. Now, there's an idea of, obviously, we do have conservation of the elements when we have a chemical reaction occurring, because in a chemical reaction, the only thing that's involved is essentially we break all the bonds and then we remake all the bonds on the other side. So since bonding is all about electrons, we have that conservation of those elements from one side of the arrow to the other side of the arrow. And that's because we're not dealing with anything in the nucleus. So if you remember, out of the protons, electrons, and neutrons, which one is most important in terms of what element it is? It is the protons, right? The atomic number. So since chemical reactions do not deal with the nucleus or protons, only electrons, we have the same elements we start with as the same elements we end with, because we don't touch anything in that nucleus. Now, when we do look at this equation, we can read this equation a couple ways. Molecular hydrogen reacts with molecular oxygen to yield water. The arrow means to yield or to form or to produce. This is also an important idea. Remember that if you have things in words, for example, which is very common, you want to make sure you get the correct formulas down. So sometimes people will see like hydrogen or hydrogen gas and forget that it is a diatomic molecule. So you want to make sure that you write H2 rather than just H, or even the same thing there with oxygen as well. You want to make sure you get O2 and not just O. So that's a very common mistake people will make, especially when you have to write the formulas down. We'll talk about this a little bit later on in this chapter when we're balancing, but that is also important to do before you do any type of balancing of the equation. And oftentimes people screw up because they try to do both things together. They try to kind of balance the equation and write the formulas, and they end up with the wrong formulas and things that do not balance. So the order that you should always follow is forget about the balancing first, get the right equations down, and then go back and balance. Never try to do them together. Usually will lead to like the wrong formulas as well. Now, when we look at this equation, there's something wrong with it. And what's wrong with it is what we've been talking about. Because we're not dealing with anything in the nucleus, there is going to be that conservation of the elements. So we should end and start really, or start and end, I guess is a better way of doing that, with the same number of elements. So for example, and when you go to balance an equation, a really good approach is to make just a little table, reactant side, product side, and then just the elements that are involved. And in this case, we could look on the left, and that 2 means that we have 2 hydrogens. That 2 means we have 2 hydrogens on the right. On the left-hand side, we have 2 oxygens. And with nothing written there, that means that we have basically 1 oxygen. So by just making this little table, we could clearly see that it is not a balanced equation. So for example, here to balance the oxygen, we could put a coefficient in front of water. And when we do balance an equation, that's also really important. It is only the coefficients that we change. We never change any of the subscripts like that 2, because if I change the 2, is that still water at that point? It is not. So you change, what it is. So only the coefficients, only the numbers in front you should change. You also should never do anything weird that people do, like put a big number in between or anything like that. So don't do that. Only the numbers that come in front. In this case, when we do put a number in front, it does go to everybody behind it. Yeah. So in this case, on the right-hand side, I now have 4 hydrogens and 2 oxygens. And this is also a very common thing that occurs when you go to balance an equation. You fix one thing, kind of screw up something else. And that means that we can still using a table is kind of helpful, because it kind of puts you in the right path as to where you should go next. And we could go next over here and just put a 2 in front of our hydrogen. That's going to give me, once again, 2 times 2 is 4, and 2 oxygens. Now we have the balance equation. So I cannot stress this enough that whenever you have an equation, you write an equation, whatever it may be, it always should be balanced. So regardless of pretty much whatever you're doing in chemistry, you need that equation to be balanced. And I would highly recommend that if you see numbers in the equation, like coefficients, you should take a look at it. I would think it probably will be balanced unless somebody's trying to trick you or something like that. I would definitely take a really hard look at it if you do not see any coefficients in front, for sure. Do you have a question? It is, yeah. So that's a really important thing, as I was saying before. It's very common, especially if you're giving things in words, which sometimes you are. People, when they see hydrogen, hydrogen gas, oxygen gas, they just go H and O, without that. So these are things that how they naturally come, right? Like hydrogen, oxygen, nitrogen, for example. Any of the halogens, chlorine, bromine, iodine, they come as twos, and you want to make sure that when you put them into the equation, they go that way. Otherwise, again, you're going to have trouble balancing. You won't have the right formulas and stuff like that. So it's really important to always start with the right formulas. And sometimes people, again, want to kind of combo everything together, and they usually end up with the wrong formulas and the thing won't balance. Other questions? And again, the purpose of that is the law of conservation of mass. Whatever we start with, we should definitely end with. And as we see here, we could fix this by putting our 2 in front of each of those to get us to our balanced equation. So up there does represent our balanced equation. Let's talk a little bit more about some of the parts of this balanced equation. As I mentioned before, everything on the left-hand side of the arrow are reactants. And that is your starting material in a chemical reaction. And everything on the right-hand side of the arrow are your products, which are formed as part of a reaction. Again, the right formulas are really important. It's even in a situation, as we will see, something like this, where, maybe you have the left-hand side and you need to write the right-hand side of the sort of equation. Again, people try to balance and write the right formulas. So always formulas, then balance, especially if you're predicting something on the right-hand side. We will talk more about this in a later chapter, but some of the relationships that we could get for a balanced equation, which is really important. We could look at these coefficients, which is where all these numbers come from. And that would tell us there's 2 molecules of H2 react with 1 molecule of this 2 molecules of H2O. Probably the relationship that we will use the most, as it is part of what is referred to as stoichiometry calculations, is this mole to mole relationship, which again also just comes from the coefficients. And we can say there are 2 moles of H2 react with 1 mole of O2 and 2 moles of H2O. The last is that conservation of mass. Because we have the same elements on the left and the right, we should end up with basically the same grams of each of those, as the hydrogen on the left is basically 1 gram, hydrogen on the right is 1 gram, and the oxygen on the left is 16 grams. The oxygen on the right is 16 grams. When we get into stoichiometry, which uses this mole to mole relationship, nothing of those calculations are going to be correct if you do not start with that balanced equation. So again, that's why it's really important. Always just make sure that equation is balanced. Let's talk about some other information that we could actually get from a chemical equation. The states of everybody. So S is the solid state, which is typically written next to the formula. L is in the liquid state. G is the gas state. I think we talked about when we talked about acids, but AQ is the aqueous state, which is basically a water environment. So very commonly we'll see these different states written next to the formulas, which can be really helpful in looking at a chemical equation to help you understand what is going on. And that is because on the bottom there, sometimes we will use chemical equations to represent physical processes or physical changes that are going on. We definitely use chemical equations to represent chemical changes that occur, but we could also use it to represent basically physical processes that are occurring, or physical changes. Like if we took water in the liquid state to water in the solid state, that's basically the process of freezing, which is a physical change. Here we basically have water on both sides. And the states are really important here because we could see that's going from liquid water to solid, which is ice. So we know freezing is going on. Without the inclusion of the states in this particular case, it would just be water on both sides, and we're not really sure what is happening, right? We don't know what state is going from on each side or if it's in the same state. We also see that on the bottom there, we have water in the liquid state going to water in the gas state, which is like steam. That's evaporation or vaporization, but that is basically what happens when you boil water. So once again, the states are oftentimes really important as well, because it does allow you to understand maybe what is happening. Yes. It does. We're going to talk about aqueous in 1 second, which I think might answer your question, and the difference between that and liquid in just a second here. Other questions? All right, so let's talk about some other things, which is sort of your question as well. We also can sometimes see water above there, which the arrow, which would indicate that we're dissolving something in water. So I think your question, and to answer your question, there is a difference between the liquid and something that is aqueous. And the difference is if something's a liquid, that's a pure substance. Like water, for example, that would have the liquid denotion. It's just water by itself, nothing else in there. Now, if you took a pure substance like water and you mix it with the sodium chloride, which is a solid, which is basically salt, we know the sodium chloride will actually dissolve into the water part. And those two things together will give you a sodium chloride solution that is aqueous. So aqueous is usually for a solution that's made up basically of two things, a solvent and a solute. Solute is the smaller part of the solution, solvent's the larger part. So here, this would be our solvent. This would be our solute. That's our larger and smaller. So a solution is typically the ones to get the aqueous symbol. It's all those bottles of sort of solutions that you use in lab that you drop out of those dropper bottles. What's confusing to people is they're both in the liquid state. But to be aqueous, you basically need to take something and dissolve it in something else. So like you dissolve the salt in water, gives you a solution. That is a homogeneous mixture is what a solution is. So that's really the definition of it. And if you remember, a mixture is the combination of two or more substances together. So that's basically the difference between something that is aqueous and something that just has the liquid sort of state to it. Other questions on that? Now, other things that we typically will sometimes see on top of the arrow. We'll sometimes see a little delta symbol that sometimes refers to heat, that you're heating something. Very commonly as well, on top of the arrow, we will see a catalyst. And a catalyst is not a reactant. It's not a product. And it does not get used up in the reaction. It is there usually to make the reaction occur faster. So it basically speeds up the reaction and makes it occur a lot faster. And very commonly, you will see it written on top of the arrow. It may be a metal, for example, something like platinum. It may be like a solution like H+, which means an acid catalyst. If you remember, I think when we talked about energy, the way a catalyst works, it lowers that activation energy hill, basically, to get from one side to the next by finding a more efficient pathway for the reaction basically to occur. So that's very commonly seen on top of the arrow. The catalysts are written. Any questions on that there? Okay, so as we talked about, we do want to make sure that the equations are balanced. So let's talk a little bit about actually balancing these equations and really the steps to do that. So there are a couple of different ways that you can go about balancing equations. One way is definitely if you're given anything in words, again, as we've been talking about, want to make sure you start out with those correct formulas first and then do the balancing. Once again, we balance by only changing the coefficients, which are the numbers that come in front of the formulas. Truthfully, most people do sort of a trial by error, put some numbers down and see what happens. Personally, I go with the whatever seems easiest to balance first and maybe save something that looks a little bit more complicated for the end. Some people like to try out with the more complicated first and then go to the less complicated. So either way is okay. There's basically two things you got to make sure of when you balance an equation. All the coefficients need to be whole numbers. And they also need to be the simplest set of whole numbers, which means let's just say we balance an equation 2a plus 4b goes to 6c. And we'll just say that this is balanced. Now, although it may be balanced, when we look at the coefficients here, I could do what with all those coefficients and still get whole numbers? I could divide them all by 2. Yeah, I could go through really and divide them all by 2 and still hit whole numbers of like a plus 2b goes to 3c. So this would be the properly balanced equation. So you should always check those two things when you're done balancing an equation. Do you have all whole numbers, and can you reduce down those numbers to a simple set of whole numbers? If the answer is yes, you can, then you should definitely do that and get the right balanced equation. If you obviously cannot divide by a common number and get all whole numbers, then you're probably at the simplest whole numbers that you could have. So those are two really important things to remember. Here's another approach. If you like this one as well, this one is more looking for ones that appear only once on each side. Which is more the way I probably would do it, and then balancing the more complicated ones towards the end. And again, the important part here is just to make sure that you have it balanced at the very end. All right, so let's take a look at an example here together, and I'll show you sort of the way I would approach it. So if we have this equation, I'm just going to rewrite it to give me a little bit more room here. So again, I highly recommend perhaps a table. It can be very helpful. So on the reactant side, product side, we're just going to write our elements: nitrogen, oxygen, hydrogen. On the left-hand side here, we got 1 nitrogen. Right-hand side, we have 2. Left-hand side, we have 1 oxygen. Right-hand side, we have 1 oxygen. Left-hand side, we have 2 hydrogens. And right-hand side here, we have 2 hydrogens. So the nice thing about the table is it gives you some direction as to where to start rather than just kind of laying up some numbers and hoping for the best. So clearly here from our table, we can see that everything is balanced except for our nitrogen, which means that's probably a pretty good place to start. So in this case, we have 1 nitrogen on the left and 2 on the right. So to fix that, once again, we can only change the coefficients, which are our numbers in front. So we would put on the front there on the left a 2. And when I put that coefficient, as I mentioned before, it does go to everybody behind it. So that would give me 2 nitrogens. Also would give me 2 oxygens, and I still have 2 hydrogens. So as we talked about earlier, pretty much very common. We fix one thing, sort of mess up something else. The nice thing about the table is I could clearly see that perhaps oxygen would be a good place to go to next, since everything else is balanced. So I could go to the right-hand side where I have my oxygen. And again, I'm going to put a 2 in front of that, and that will go to both of the things behind it. So that's going to give me 2 nitrogens. I now have 2 times 2, which is 4 hydrogens, and 2 times 1, which is 2 oxygens in this case. At this point, I got everybody balanced except for the hydrogen. And now I can see I just need to go back to the left-hand side there and put a 2 in front of there. And that's going to give me my 2 nitrogens, my 2 oxygens, and my 2 times 2 is 4 hydrogens. And now I do have a balanced equation. Any questions on that there? Yeah. So if you put a number in front, it goes to everybody behind. And you got to distribute it to everybody. And you can see you kind of go back and forth. Eventually, everything should fall into place. If it's taking you an hour to do one equation, you probably have a wrong formula probably somewhere, I'd imagine. All right, let's try one there yourself. Why don't you give this one a go? Balance up this equation, see what you end up with. Okay, let's take a look. So once again, I'm just going to make a little table. And again, I feel it nicely organizes for a lot of people. Carbon, hydrogen, and oxygen. So on the left-hand side here, we have 3 carbons. Right-hand side, we have 1. Left-hand side, we have 8 oxygens or hydrogens. Right-hand side, we have 2. Left-hand side, we have 2 oxygens. And left-hand side, we have 2 oxygens there, plus 1 more there, gives me 3. So you don't want to forget the guys are in different sort of spots. So in this case, not much sort of balance. So we do have a lot of options to maybe where you could start. Personally, I'm just going to go with what seems pretty easy to fix based on my table. And what I can see here is carbon looks pretty easy to fix. It's just on one thing on the right and left. So I could fix the carbon by putting a 3 in front of it. Once again, that does go to everybody behind it. So that's going to give me 3 carbons. Still 2 hydrogens. Now in terms of oxygen, I got 6 working there from the first guy. And I still got 1 more on the outside there, which is 7. Any questions on that there? Yeah. What's that? The coefficient in front tells you how many of those elements you have behind it. You have to multiply it by everybody that's behind it. So the 3 doesn't just go for the carbon here in this case, it also goes for the oxygen. So you have to multiply it by 3 times 2 in this particular case for the oxygen. Yeah. Other questions? Okay, so now I got the carbon fixed. I have a choice of hydrogen and oxygen. Why am I going to choose hydrogen first, you think, in this case? Where's oxygen on the right-hand side? It's in a couple of things on the right and 1 thing on the left. So that's a lot of things together with oxygen, right? If we look at the hydrogen, we just got it in 1 place on the left, 1 place on the right. So that's a little bit more simpler. We could fix the hydrogen without maybe messing up too much stuff. So that's why I'm going to tackle hydrogen first here, and I can make a 4 right about there. And when I do that, again, that's going to go to everybody behind it as well. That will give me 3 carbons. We will have 4 times 2, which is 8 hydrogens. Now, in terms of oxygen, we still have 6 here, but now we have 4 times 1, which is 4 here. So that's a grand total of 10 in this case. Yeah. At this point, now that I left oxygen for the end, I clearly don't want to change any numbers that I put down. I could very easily fix that by going to the left-hand side here and putting a 5 in this case. Although it may look like a 6, we'll make it a bad-looking 5. And that gives us 3 carbons, 8 hydrogens, and 5 times 2 there is 10 oxygens, and we are balanced in this case. Any questions? Yeah. Truthfully, it doesn't really matter. Personally, I would start with whatever seems the easiest. It's kind of 1 place on each side is usually a good way. As you can see here, oxygen was a couple places and 1 side and 1 place on the other. And especially when you have an element like by itself in its sort of molecular form, like O2 we have here, and then we got that element and a couple things on the other side. Usually is a good idea to kind of save that guy for the end to sort of balance and hit the other ones. But to answer your questions, you may start on the reactant side. You may start on the product side. You may have to, in some cases, start on both sides at the same time. There may be nothing balanced. In order to get somebody balanced, you may have to put coefficients on both sides to start with as well. So you may have to start either in any place. Other questions? All right, so let's try another one here. Write the balanced equation for this reaction. A little words here. Diboron trioxide reacts with water. Okay, so let's take a look. So I know the equation is given to you on your paper, but if it's not and you have just the words here, This is what we were talking about earlier. We want to make sure that we start with the proper formula. So diboron trioxide, those are some prefixes, which tells me it's type 3. So that's a little B2O3 action. Hopefully we remember water is H2O. To form there, boric acid, which was given to us. So as you can see here, I'm just writing down the equation, the unbalanced equation. I could care less about the balancing part of it until I get all the proper formulas down. Now that I do have all the proper formulas down, now I could get to the balancing part. And again, that is the proper order as to how you want to do that. So now we can make our table, and we have our reactant side or product side. We have a BOH here. All right, so left-hand side, we have 2 borons. Right-hand side, we got 1. Left-hand side, we have 3 oxygens there, plus 1 more there is 4. Right-hand side, we do have parentheses and a number on the bottom, so that does get multiplied into everybody that's inside the parentheses as well. So we will have 3 oxygens. And on the left-hand side there, we have 2 hydrogens, and we will also, again, have 3 hydrogens in this case. At this point, there's not much to work with, so I'm going to go with the boron, which seems to be the easiest. And I can simply balance the boron by putting a 2. That 2 now gives me 2 borons. It goes to the boron. It also goes into the parentheses as well, which means that is 3 times 1 times 2, which is 6 oxygens, and also 6 hydrogens. So you do have to multiply in and multiply out in that particular case. Any questions on that? Obviously, at this point, I can't do much on the right, so I'm going to go to the left here to try to figure out what I want to do. And once again, I have a choice between oxygen that's in a bunch of stuff on the left and just hydrogen that's in one on the left-hand side. So I'm going to start with the hydrogen as my choice because that seems much easier to balance. And I can balance that by putting a 3 in front of the hydrogen. That's going to get distributed to both of these guys here. And that's going to give me 2 boron. Oxygen, there are 3 here and another 3 over here. That is 6. And hydrogen, 3 times 2 is 6. So in this case, by balancing the boron, it also took care of the hydrogen and oxygen. So that works really well as well. And that usually will happen. Usually everything should fall into place. Question on that one there. All right, one last one here. Balance this guy up, see what you come up with. Okay, let's take a look since we're getting to the end here. So using our table, we have 1 nitrogen on the left, we have 1 on the right. We have 3 hydrogens on the left and 2 on the right. Got 2 oxygens on the left, and again, we do have 2 oxygens right there on the right-hand side. So in this case, everything is balanced except for the hydrogen. And as to the earlier question, in this case, we actually do need to put a number on both sides here to begin with, as hydrogen is the only thing that's not balanced, and the common number there is actually 6 between those two. You get that by just multiplying 3 and 2 together. So to make our hydrogen on the left a 6, we do need to put a 2 there. To make our hydrogen a 6 over here, we do need to put a 3 over here. So in this case, we do actually have to put numbers on both sides to begin with. When we do so, again, distributing that 2 to everybody behind it gets me 2 nitrogens, 6 hydrogens, and 2 oxygens. Also distributing over here gets me 1 nitrogen, 6 hydrogens, and I have 1 oxygen there and 3 more there, which is 4 in this case. Any questions on that there? At this point, we fixed the hydrogen, but pretty much screwed up everything else. So the next easiest thing to balance, once again here, is going to be the nitrogen, as the oxygen clearly is in a bunch of places. So we want to leave that maybe for the end. So I'm going to go to the nitrogen where I can put a 2. And again, distributing that out will give me 2 nitrogens, 6 hydrogens, 2 oxygens, and 3 oxygens there, which is 5, and 2 oxygens on the left there. So to fix this, we do need to make basically our 2 into a 5, and we definitely don't want to touch any of the other numbers there, as that's going to screw up everything. So in this case, we could fix it by using a fraction, which is 5/2. And if we do that, that will give me 2 nitrogens, 6 hydrogens, and once again, when I take 5/2 times 2, that is going to give me 5 for our oxygens. Now, in this case, this equation is balanced, but is it correctly balanced? It is not. Cannot have a fraction. So you can use a fraction like this one demonstrates to balance the equation, but you do need to get rid of the fraction by multiplying everybody by the coefficient, which will give me 4NH3 plus 5O2 gives me 4NO and 12H2O. I'm sorry, 6H2O. As we distribute that 2 all the way across. And if I didn't screw it up here, we should still be balanced. We have 4 nitrogens on both sides. We have 4 times 3, which is 12 hydrogens. 6 times 2 here is 12. And 10 oxygens and 10 oxygens. So you can use a fraction to balance it, but you do have to clear it. If you're not sure how to choose the fraction, top number is the number you need. Bottom numbers should match that number, and you'll always pick the right fraction in that particular case. Any questions on that? All right.